Kinetics HL2, reaction mechanisms. Essential ideas. Rate expressions can only be determined empirically, and these limit possible reaction mechanisms, in particular cases, such as linear chain of elementary reactions, no equilibria, and only one significant activation barrier. The rate equation is equivalent to the slowest step of the reaction. Nature of science. The principle of Occam's razor. This principle says that newer theories need to remain as simple as possible while maximising explanatory power. The low probability of three molecule collisions means stepwise reaction mechanisms are more likely. Theory of knowledge. Reaction mechanisms can be supported by indirect evidence. And here we can have certain questions such as, what is the role of empirical evidence in scientific theories, or can we ever be certain in science? So what are reaction mechanisms? Well, chemical reactions occur by a series of smaller steps that make up a reaction mechanism. Here in example 1 we can see the natural depletion of ozone. You can see here that ozone in step 1 undergoes homolytic fission because of UV light, and it splits into oxygen and oxygen molecule, oxygen free radical. Then that in step 2, ozone then reacts with the oxygen free radical, the very reactive species, to give 2 oxygen molecules. The overall reaction will be as so. In example 2, we've got CFC, catalyzed depletion of ozone. We've got the initiation step, where you see dichloro-difluoromethane giving CF2Cl and the chlorine free radical. Ozone then reacts with the chlorine free radical in the presence of UV light to give this chlorine oxygen free radical and oxygen molecule. This chlorine oxygen free radical then react with an oxygen free radical to give chlorine free radical and oxygen. But if you did the overall reaction, we'd get ozone reacting with the oxygen free radical to give us 2 oxygens. And so you've got 2 different reactions and different mechanisms that take part in said reactions. Let's have a look at this equation at the top here. We've got a manganate ion reacting with an iron 2 ion and a proton. If we just put in the coefficients, we'll balance that. You can see that if this reaction to occur in one step, there's going to be a whole many particles need to hit each other at the same time. I mean, if you think about it, to make water, you'd need 2 of these hydrogens and 1 of these, because that's where oxygen is, to hit each other at the same time to make this. The iron is going to have to hit here to lose another electron to become iron 3+. So that's going to happen at the same time too. And then the manganate, this thing here, is going to have to be handing over electrons and losing oxygens to the hydrogen. So a whole bunch of things need to collide together for this to occur. If it were a single step, it's extremely unlikely. So the low probability of 3 molecules or more collisions means stepwise reactions are more likely. You do get some 3 molecule collisions, but they're extremely rare, and above that, almost non-existent. Most chemical reactions occur in a series of small individual steps involving 1, 2 or 3 colliding molecules. Some terminology. Elementary processes. These are the individual steps in a mechanism. Molecularity of an elementary process. This is the number of reacting species. Unimolecular means 1 reactant species. So it'd be 1 molecule, atom or ion. Bimolecular means 2 reactant species. And termolecular, which is very rare, would be 3 reacting species. 3 things colliding at a single point in time for a reaction to take place. Reaction intermediate, a species formed in an early step but consumed in a later step, and it doesn't appear in the overall equation. So it's neither really a reactant or a product. It exists somewhere in the mechanism, but you don't have it to start with, and you don't have it at the end of the reaction. It's an intermediate. Let's have a look at the natural formation of ozone. Step 1, we've got oxygen splitting because of UV light to give 2 free radicals. It's oxyunimolecular because we've only got 1 oxygen molecule involved. This one, we've got oxygen in step 2 and a free radical giving us ozone, and 2 reactants, so it's bimolecular. And you can see the starting product, oxygen, and the finishing product, ozone. The intermediate, this free radical, is neither a reactant nor a product, so therefore it is an intermediate. It doesn't exist at the beginning and it doesn't exist at the end. Next, we have a catalyst. And this is a species used in an early step which is regenerated in a later step. Okay, so unlike when we looked at intermediates, which didn't exist at the very beginning or at the end, a catalyst both will be present at the very beginning, at the initial step, and you can see here, it's also present in the final step. So it isn't used up. A species used in an early step and which is regenerated in a later step. So the nitrogen dioxide catalyzed depletion of ozone. We've got intermediates. You can see here the nitrogen monoxide and the free oxygen free radical are created in the first step, but they weren't there to begin with. Okay, you can see them in step 2 and step 3. And they're being used in step 2 and step 3, they're being used up. So they're created in step 1, being used up in step 2 and step 3. Conversely, nitrogen dioxide here, that is present at the beginning of the first step, and it's used up, but then it is regenerated at step 3. Okay? And the overall reaction is here. And sometimes you'll see people write the catalyst just above that arrow. Example 5, we've got hydrogen peroxide decomposition. You can see here that we're using up the iodine ion. So it's present at the beginning of step 1, and then it is formed in step 2. It's a product in step 2. So it's regenerated. It's a catalyst. The intermediate iodine oxide, that'll be right, ion, is created in step 1 and then it's used up. So it's an intermediate. So I think you got the idea. The difference between an intermediate and a catalyst. Intermediates or steps in a mechanism can be proposed. Let's have a look at this. Example 6. We've got carbon monoxide reduces nitrogen dioxide to produce carbon dioxide and nitrogen monoxide. So what is the overall equation, first of all, and then complete the steps. And this is the right way to do it. First of all, write out the overall equation from the information given in the question. So we've got carbon monoxide reducing nitrogen dioxide to give carbon dioxide and nitrogen monoxide. So there we go. We've got the nitrogen dioxide, we've got the carbon monoxide, we've got carbon dioxide being formed, nitrogen monoxide being formed. So now we've got to work out what could be the intermediates, or are there any catalysts? So we can see here that what we want is probably reduction and oxidation to take place. We want an oxygen from one molecule to go to the other molecule. So one molecule will be oxidized up to nitrogen trioxide, one will be reduced to nitrogen monoxide. Then the nitrogen trioxide here is an intermediate, you want the thing to cancel out, and it is going to react with the carbon monoxide here to give carbon dioxide and nitrogen dioxide. You can see that the nitrogen trioxide are indeed intermediates because they cancel out, and also the nitrogen dioxide, one of the nitrogen dioxide as the reactant, will cancel out too. Then you have your Step 1, nitrogen dioxide with carbon monoxide, given carbon dioxide and nitrogen monoxide. Okay, next, example 7. Nitrosyl chloride, NO2Cl, decomposes via this two-step mechanism to form nitrogen dioxide and chlorine. First of all, we'll work out the overall equation, then complete the steps. So we'll just write in what it gives us in the question, or in the example in this case. So we've got the nitrosyl chloride, gives us nitrogen dioxide and chlorine, balance the equation, and then we've got to try and think of what's going on here. Okay, so we do definitely want nitrogen dioxide to be formed, so that's good. In step 2, we know that we need to make some chlorine. If we're making nitrogen dioxide here, then the chlorine gas is going to be released, or it's going to be, sorry, the chlorine atom is going to be separated from the nitrogen dioxide. Then the nitrosyl chloride will react with that free chlorine atom to form nitrogen dioxide, and the two chlorines will react together to form chlorine gas. We just double check, right, by cancelling out the intermediates. Sometimes more than one reaction mechanism can be proposed, and both are possibilities. Here in example 8, we've got carbon monoxide reducing nitrogen dioxide to produce nitrogen monoxide and carbon dioxide. And you can see it. This and this are the same, but you can see as well that we've got two different proposed mechanisms. The reaction mechanisms are like hypotheses and need to be verified or refuted by experimentation. Here we've got the nitrogen dioxide and nitrogen dioxide forming N2O4. The N2O4 then reacts with the carbon monoxide to give us nitrogen monoxide, carbon dioxide. Conversely, here we've got a homolytic fission of nitrogen dioxide to give us nitrogen oxide and the highly reactive oxygen free radical. The carbon monoxide would then react with a highly reactive free radical to form carbon dioxide. Okay, both are acceptable hypotheses. Every reaction mechanism has one step that slows down the process. The reaction can go no faster than this step, which is called the rate determining step. If you speed up the faster steps, will the overall reaction be faster? What do you think? If you speed up the slower step, will the overall reaction be faster? Let's have a look, let's have a think about that and then try and resolve these fascinating questions. If you describe an event in your day as a reaction mechanism, such as waking up and leaving your flat, taking a trip to school in the morning after leaving your home, or getting out of arrivals area after landing at gate 30 at Czechoslovakia airport, you might then start to understand how a slow portion of any of these things will have a massive effect compared to other things. So press pause, scribble down a paragraph of one of those three things and see if you can highlight the rate determining step. Okay, the trip to school in the morning after leaving your house. I can do this one. After I've woken up and I've crushed my 1,000 push-ups and 1,000 sit-ups and 1,000 squats, I jog downstairs, run to the ferry, get on the ferry, start reading some chemistry manuals, jump off the ferry and then sprint to work. You can see that the rate determining step here, the thing that slowed me down the most was the trip on the ferry, because it was a set speed and it goes much slower than the other parts of the day. I could do the push-ups faster, I could do the squats faster, which means that would be quicker. But the real rate determining step, the thing that always slows me down, is how slow this ferry goes. It will always go that slowly unless I was to attach some rope to it, get in front and drag it by doing front crawl. Okay, so the rate determining step controls the rate of a reaction at a given temperature. Speeding up a fast step in the reaction does not increase the overall rate of the reaction. speeding up the slower step in the reaction will increase the overall rate of the reaction. Let's consider this mechanism for the reaction A2 plus B2 equals 2AB. Step 1 is slow. A2 splits into A and A. Step 2, A then reacts with the B2 molecule to give AB and B, which is a fast reaction. Step 3, A plus B gives AB. If the concentration of A2 is increased, will the overall rate increase? Well, if we look at what we've just written down up here, if you increase the concentration of this, then yes, we know increased concentration increases the rate of reaction, and since this is the slow part, increasing the rate of the slow part will increase the overall rate of reaction. Conversely, if the concentration of B2 is increased and A2 isn't, then the overall rate will not increase, because you still have to have this slow process occur before the fast process can occur. So this will determine the rate. So the concentration of B2 will not affect the overall rate of the reaction. Think back to rate expressions. The rate of reaction at a given temperature depends on the order of the reaction. And then think about what we've just discussed about the rate determining step. The rate of a reaction depends on the rate determining step. Is there a connection between the two? Well, as you can probably guess, there is, or I wouldn't have mentioned it. Given this reaction, 2A plus B gives C plus C and D, the experimentally didn't say that right. The experimentally verified rate expression is rate equals K concentration of A. Is there a relationship between the coefficients in the overall equation and the order of the reaction? No, there is not. Let's consider the experimentally verified mechanism for this reaction. You can see step 1 is A goes to X. Step 2 is B plus X gives Z plus C, and 3 is A plus Z gives D. Only the slow part of the mechanism determines the rate. So only the slow step should be used when forming a rate expression. So you only need to look at the slow step in this case. So is there a relationship between the molecularity of the rate determining step and the order of the reaction? Well, the order of the reaction is 1, and look at this coefficient. There's only one of these. So you can see a link. The coefficient, if you had your little m there, it would say 1. And if you had your coefficient written out here, it would be 1. So there is a link. The rate expression, the order with respect to A is 1, and the order with respect to B is 0. There are no, B does not exist in the slow step. And so it will have no effect on rate, and so you wouldn't include it in the rate expression. That makes sense, right? So, the rate determining step, step 1, is where you form your rate expression. The molecularity, or the coefficient of A is 1, and so the coefficient there, you can just stick it up the top there as 1, and B is 0, so you wouldn't include it. We wouldn't include it because B to the power of 0 is 1, so you don't include it. Deducing the rate expressions for mechanisms. The order of the reaction can be predicted from the molecularity of the rate determining step. Example 1. The rate determining step is the first step of the mechanism. Predict the rate expression for the depletion of ozone given this mechanism. So example 1 is easy because the RDS is the first step. So we've got ozone, which is being chopped up into a molecule of oxygen and an oxygen free radical, and nice, very pleasant to see this as our first step being the slow step. Let's state the general rate expression for the overall reaction. Well, there's only ozone in the slow step. So when we put rate equals K, concentration of oxygen, and put a little m there for now, and then we're going to determine what it is. Then we use the rate determining step to predict the order we can see in step 1, we can see the coefficient of ozone is 1. We could write it there if we really wanted to, but we don't need to. And so m equals 1 because it is the coefficient. So that would be the rate, the rate expression. Next, this is a bit less easy. The rate determining step is the second or latest step in the mechanism. We're going to predict the rate expression again for this reaction. A plus 2b gives C, given this mechanism. You've got two B's reacting to give Q in a fast reaction. Q then reacts with A in the slow reaction to give C. So we're going to state the general rate expression for the overall reaction. And we need to be careful here. We're going to put K, A to the power m and B to the power n. Okay? And you might be thinking, why are we putting B there? Why are we putting B there when clearly B is not in the slow step? Yes? Well, just bear with me. The rate determining step is step 2. And so the coefficient A is definitely 1. And the coefficient of Q is 1. But we can't include Q in the rate expression because it's just an intermediate. Okay? But we do know something about Q. What do we know about Q? Well, Q is produced in step 1, and so step 1 has to occur for Q to form. And in this case, we'd have to replace Q with the reactants that formed it. In this case, which is B. And there's 2 of them, isn't there? There's 1, 2. There'll be a 1 there. Sorry, be a 1 here. Be a 1 there. And so when we're doing N here, we'd have to include both. So it's going to be 2, second order with respect to B. So the rate expression would be K, B to the power of 2, A to the power of 1. Okay, I'd like you to press pause and complete these 2 practice questions. Just have a go with them. First thing you do, predict the rate expression, just write it out. Then you predict the effect on the rate when the concentration of both reactants doubles. Okay, so did you get the following? Let's have a look. You've got the overall equation. So we can cancel out the nitrogen trioxide, cancel out the nitrogen dioxide to get this overall equation. Predict the rate expression. Look for the slow one. You can see there's only nitrogen dioxide there. And you can see there's 2 of them. 1, 2. So we know that the coefficient, so the power that we'd use for the order would be 2. Predict the effect on the rate when the concentration of both reactants doubles. So if we double carbon monoxide, nothing happens because it's not part of the rate expression, because it's not part of the slow step. However, there's 2 nitrogen dioxides in the slow step. So if we change 1 here to 2, get 2 squared, 4. So the rate will be times 4 if you double the concentrations. Practice question 2. We've got the slow step here. And so oxygen will be 1. But you can see straight away the N2O2 is an intermediate. Okay? And so we can't include this in the rate expression. So you need to look at what formed this. And in the fast step here, you can see 2 nitrogen monoxide molecules formed this. So we need to substitute in for this, these 2. 1, 2. So the order will be second with respect to that. And first order, because there's only 1 here in the slow step, for the oxygen. Now if we were to double both, we need to double the nitrogen monoxide and the oxygen. So if we just put 2 in there instead of nitrogen monoxide, put 2 in there instead of oxygen, 2 squared is 4, 2 to the power of 1 is 2, 4 times 2 is 8. It's going to be 8 times, an 8 times increase. Next, deducing mechanisms from rate expressions. This experimental data for the order of the reaction can be used to support or refute a proposed mechanism. Given the hypothetical reactions 2A plus B gives you C plus D, the experimentally verified rate expression is rate equals K, A concentration of A squared, concentration of B. Which of the following would be a mechanism for this reaction? Let's have a look one by one. First of all, mechanism A. We've got slow as first, nice and sweet, and we've got A there and B there, so it's going to be A1, B1. A1, B1. So that one's no good. What about this one? Slow as second, which is what we want. So we've got X as an intermediate, so it wouldn't include that. So we're going to have A1 here in a slow step, but X is formed in a fast step by 1A and 1B. So we've got two A's required, so A to the power of 2, B to the power of 1. So that one kind of matches. Next, slow, just two A's, no B, so that's no good. This one, we've got slow, A squared. Oh, so it's not A squared, it's molecule, diatomic molecule of A. So we've got B, power of 1 is good, and this molecule is being formed, it's being used in the slow step, but it's not in the overall rate expression. So how was it formed? It was formed from two A's in the fast step, so we'd need to include these two A's. So it's going to be A to the 2, B to the 1. So that one's good too. Next, 3 steps. Got B going to X is a slow one. What forms B? Nothing. And so we'd have B, only B, because this is the only reactant in the slow step and it's not relying on anything. Yeah, splendid. So we've got that one and that one will be good. Okay, SN1 reactions for tertiary halogenoalkanes. You can see here we've got let me just think what the name of this thing is. It's 2-bromo, 2-methyl propane, I believe. And we've got this nucleophilic substitution reaction going on. The slow step is where the stable carbocation is formed and the bromine ion is released. So there's one reactant in the slow step. How would we say it now that we have some fancy nomenclature? We would say that the rate determining step is unimolecular. And we know that the rate expression would be just this here. The energy level profile, you can see, and we're using chlorine instead of bromine this time, but it doesn't make a difference. We've got this great big activation energy to start with, forming the complex where you've got this very, very, unstable molecule where you've got the strong dipole formed and the chlorine's keen to leave. Then the carbocation forms, and this is slightly stabilized, so it's a lower energy level. Then the nucleophile will come in and the intermediate species would form here again, which is less stable, and then the bond forms fully and you get the alcohol formed. You see step 1 here, the rate determining step, it has a higher activation energy. Okay, it's a slower step because it has a greater activation energy. The faster step has a smaller activation energy. Here we've got another nucleophilic substitution reaction, SN2 reactions for the primary halogenoalkanes. You can see the slow step is the first one, and you can see straight away we've got 2 reactants. So we might have said that there are 2 reactants in the slow step before, but now that we are experts, we would use correct nomenclature, and we would say that the rate determining step is bimolecular. The slow step, or the rate determining step, is bimolecular. So what would be the rate expression? Well, it's going to be both of these reactants in there. And you can see there's one each, there's one of that, one of this. So M would be 1, N would be 1. And you can see here in the energy level profile, the activated complex transition state has a very high activation energy because it's pretty unstable. Okay. I'm sorry. Do you want to talk about that a bit more? You've got your starting products, high activation energy, leaping up, unstable complex transition state, and then ghostly products down there. Another multi-step reaction here, what a 3-step reaction. Let's say read the notes for this one. The rate determining step is step 2. Why is this? That's correct. It is step 2 because this has the highest activation energy out of this step here. The activation energy of step 1 is smaller than the activation energy of step 2. And the rate determining step also has the highest activation energy. Also, the enthalpy change for the overall reaction is totally independent of the mechanism involved. You could go any other route you want to. The reactants have this enthalpy, the products have this enthalpy, so the enthalpy change is the same regardless of mechanism. The valley between the hills represents the energy needed to form the reaction intermediate. Okay, so this valley between the hills, there to there, of reaction intermediates. And the top of each hill represents the energy needed to form the activated complex. So at each point here and here, you have reaction intermediates, and at the top of the hill, you have activated complexes. Here, one more look at a multi-step reaction. You can see that the uncatalyzed reaction has a high activation energy to the top of the peak. A catalyst provides a different reaction mechanism with a much lower overall activation energy, and you can see here the first activation energy is about half of the other one. It's providing a different route to take, which requires less energy. The output, of course, the overall enthalpy change for the reaction doesn't change whatsoever when a catalyst is added. Okay, and that's the end of that presentation. Splendid.